Hello everyone, today we'll speak about activation energy and Arrhenius equation. Let's get started. So to calculate the activation energy, we can use Arrhenius equation, which is not only representing or showing the activation energy, but it's also showing the other requirements for a reaction to happen. The collisions between particles, the correct orientation, and finally the activation energy. So here's Arrhenius equation. We have K, which is equal to A, e to the power negative EA over RT. We don't have anything new here except for the A. So this formula is studying the requirements needed for a reaction. A, which is the new thing that we have here, which is Arrhenius constant. This number is representing the likelihood that collisions would occur with the proper orientation for a chemical reaction. Other than A, we have EA, which is the activation energy. We have T, the temperature in Kelvin. We have R, which is the universal gas constant, 8.31, and it will be always given in the data booklet. Before we start speaking about Arrhenius equation and how we should implement it or use it in problems, we have to agree about some basic points. First of all, Arrhenius equation is an empirical relationship. It cannot be proven mathematically. E to the power negative EA over RT is known as exponential factor and represents the fraction of the reactant particles that have sufficient energy to react. We can use here a simple example. If this e to the power negative EA over RT is equal to 2.5 multiplied by 10 to the power negative 6, it means that in a million collisions, we have 2.5, only 2.5 collisions have the activation energy, We can see also that A, the frequency factor constant, it is a constant. It relates both the frequency of collisions and to the steric factor. Steric factor is the geometric alignment or the correct orientation, which is the fraction of the collisions between reactant species that have the correct orientation in order to react. E to the power negative EA over RT has no unit. So the frequency factor A, will have the units of the rate constant. So A, the unit for A is based on the unit for K. If you can return back, think about K, we already calculated or found out the unit for K based on the order of the reaction. So we have to always consider that when we are aiming at finding the unit for A. Now, how can we use Arrhenius equation to calculate the activation energy? First of all, we can manipulate the Arrhenius equation to be written as the following. ln K is equal to negative EA over R multiplied by 1 over T plus ln A. If we have data about both the rate constant K and T, the temperature in Kelvin, we will find something which is really interesting. The graph which is plotted for ln K against 1 over T is representing a straight line. This is not something which is like strange, because this equation that we have here is matching with the straight line equation. For that reason, from this equation, we can see that the gradient of the straight line is equal to negative EA over R. So we can easily calculate the activation energy if we have a graph, if we have a graph for ln K against 1 over T, because the gradient will represent the value for negative EA over R. Then we can figure out the value for the activation energy, as we will see in the next problem. Okay, we have here a problem. Use the following data to calculate values for activation energy, EA, and the frequency factor for a second order reaction. We'll speak now about why we have been given this piece of information, second order reaction. Okay, I will look directly to the table. We have here, this table is representing the relation between 1 over T and ln K, which formula I should use. We have here, those are coming directly from the data booklet. So I don't have to memorize any formula. It's coming directly from the data booklet. But as long as I have data about 1 over T and ln K, I will directly use this formula. And if we can remember from a while, we have said that this equation here, Arrhenius equation in this form, is representing a straight line equation. What does it mean by straight line equation? If we manage to plot a graph for ln K against 1 over T, we will get a straight line. Then, if we manage to calculate the gradient, we will find the value for the negative EA over R. So let's go ahead, calculate negative EA over R, which is representing the gradient of this graph or this straight line. So negative EA over R, it will be calculated using the change in ln K over the change in 1 over T. Okay, let's use the numbers that we have here in the table. We'll use the change ln K. I will use 10.7 and 2.27. So 10.7 minus 2.27 over the change in 1 over T, which is 0.00125 minus 0.0025. We put those numbers in the calculator. We will get this number, negative 6744. We have to keep in mind that this value is for negative EA over R is equal to negative 6744. Okay, so calculating EA now should be very easy. Why? Because we'll just, so we have here negative, we'll go away with this negative, so we'll have 6744 multiplied by R, 8.31. So the activation energy is equal to 56,042 joule per mole, or we can write it as 56 kilojoule per mole. Okay, this is the activation energy. We did not finish the problem. We still have to calculate the frequency factor A, which is very easy job. Why? Because we will directly use the formula here. So ln, we could just manipulate this formula. So we'll have ln A. Let's use another color. ln A is equal to, we'll manipulate this formula. We have this part in negative, so it could go to the other side with a positive sign. So ln K plus EA over R. This is multiplied by 1 over T. Okay, let's put our numbers. What is lnk? We have here lnk. We can use this number 2.27 plus what is EA over R? Okay, we already calculated from a while the EA over R, negative EA over R, which is negative 6,744. So EA over R is equal to 6,744 multiplied by 1 over T, which is 0.0025. Don't forget to use the brackets, otherwise you might get a wrong answer. So the answer is 19. If you put that in the calculator, you'll find it 19.13. Okay, but this is LNA. How can we find A now? Is very easy. Why? Because A simply is e to the power this 19.13. You just have to put in the calculator and you will get a big number. Why big number? Because A is representing the frequency of collisions, so it has to be a big number. 2.03 multiplied by 10 to the power 8. Now let's move to the interesting part, which is what is the unit? What is the unit for A? Didn't we say from a while that A has the unit of the rate constant? We can see that this reaction is second order reaction. This reaction is second order reaction. So A will take the unit of the rate constant, and the rate constant here, or the reaction that we have here, is second order reaction. Can go back to the previous lesson to know how we can figure out the units for the rate constant for a second order reaction. It's very simple. So the unit for A is same as the unit for the rate constant of a second order reaction, which is mole to the power -1 dm to the power 3 s to the power -1. Okay, that's it. Hope you understood this problem, and see you later.